Hello everyone. So welcome back to another tutorial of PyTorch. In this series, we are discussing how to use PyTorch framework to solve deep learning problems. This tutorial explores neural network capabilities through binary classification tasks on 3 different datasets. We will demonstrate how neural architecture affects the ability to learn different decision boundaries. Core concepts covered are the following. Linear versus nonlinear decision boundaries. We will understand when simple models are sufficient and when more complex architecture are needed. We will see model capacity, how network depth and width relate to learning capabilities. We will see PyTorch implementation, building neural networks using PyTorch modular design. We'll see training and evaluation, creating robust training loops with proper validation and visualization, plotting data sets and training metrics for better understanding. All right, so let's get started. So we start with downloading the dependencies. Okay, let's just run this thing. Then, as I also discussed in my previous tutorials, we are going to use the GPU, Apple Silicon GPU. So let's run this thing just to make sure that I am using GPU, not CPU. We will define 2 neural networks. One is a simple and the other one is more complex. For simple, we are going to use this architecture with input number of features is equal to 2 because we have 2 different classes. We have one hidden layer with 5 neurons, and then we have one output neuron. In PyTorch, the way you create the class is you have to import nn.module class, then you define different parameters. Here we define layer 1, layer 2, and we define the activation function. ReLU is our activation function here, and then we define the forward function. Next is we define a nonlinear model or more complex model. Here by default, we are using 32, 16, and 8. Input size is equal to 13. Then we have 3 hidden layers. The first hidden layer contains 32 neurons, second hidden layer contains 16 neurons, and the third hidden layer contains 8 neurons. This function is very similar to the simple one. So here we are going to define the layers, and then we define the forward function. So next step is to define binary classifier class, and it handles the training and evaluation logic for binary classification. The parameters are model, device, learning rate, and also optimizer. Learning rate is equal to 0.01 and the optimizer is equal to stochastic gradient descent. However, you can choose between Adam and stochastic gradient descent. The loss function here is BCE with Logit's loss. This combines the sigmoid activation with binary cross entropy. All right. This is a train step for one iteration, single training step. This one is the evaluation. Now another class is the DataManager class. This class handles all data related operations, including generation, splitting, and tensor conversion. All right. So the first function is the generate data. It will only generate the simple data with a linear boundary, with a linear decision boundary. So in the DataManager class, we have the generate data. As I explained, it will generate linear synthetic data. This function generate circular boundary data set, and this one generate XOR like data set. Here is a function which split the data into train and validation test. This function converts the NumPy arrays into PyTorch tensor. This function is just for the plotting, and this function is for comparing the different data sets, and I will show you at the end how to use this function. Okay. Now another class we have to define is the trainer class. The trainer class manages the training process, including training loop and metric visualization. This function is the actual process, the training loop with validation. And this function is just for the plotting training metrics. All right, so now you have defined all of the main functions necessary for this tutorial. Now we have everything, so we will do some experimentation. Okay, so first I'm defining my device. I am going to use MPS, which is Apple Silicon GPU. Okay, The first part is we are going to use the linear data, and we will use the simple model to train. Here we are preparing the data. As you can see, we have two classes and we have a linear decision boundary. Split and convert the data into PyTorch tensor, initialize and run trainer, and then train and visualize. Okay, as you can see, the simple model is very good. Validation accuracy is 0.99, 99%, and you can see the training loss is decreasing over time, which means the simple model has learned to split the two classes. Let's test this model. The model accuracy is almost 100%. Very good. So we are very happy. The next experiment is using non-linear model on circular data. You can see the circular data. You have non-linear decision boundaries, and we will use the more complex architecture to learn the non-linear decision boundary. As you can see, the training loss is decreasing over time and the validation is almost 74%. Before moving to XOR, let's just do a very quick experimentation. And instead of using 0.01, let's just use 0.01 learning rate and see what happens. Loss is decreasing, validation accuracy is almost the same. Okay. So you can do the experiment by changing either the optimizer or the learning rate. Let's move on to the third experimentation. Here we are going to use simple model on XOR data. As you can see, training loss is decreasing and the validation accuracy is increasing. Okay, so what we are going to do is we will first check with this more complex architecture, and then we will experiment with the optimizer and learning rate. So let's use the same experimentation with more nonlinear model. Okay, initialize and then train and plot. Not so good. So maybe let's just try to see if we can do better by changing the learning rate. Well, yes, by changing the learning rate, it's getting better. I can do a 0.05 and see. Hey, actually, by changing the learning rate, the validation accuracy has jumped to 99%, which is pretty good. Let's just do another experiment. Instead of changing the learning rate too much, we change the optimizer. All right. By changing the optimizer, you can see the loss function goes to 0 almost, and the validation accuracy is almost 99, which is pretty good. So this means that the Adam optimizer is much better in this case than stochastic gradient descent. This occurs because the XOR problem creates a complex loss landscape with multiple local minima. Stochastic gradient descent with a small learning rate often gets trapped in these local minima, resulting in suboptimal performance. Two effective solutions we can use: increase the learning rate as we saw, or use the Adam optimizer. Adam often performs better on complex problems like this XOR because it adapts learning rate for each parameter. It incorporates momentum to help escape local minima, and it combines the benefits of AdaGrad and RMS prop optimizers. So what are the key takeaways from this tutorial? Number one, model architecture matters. The choice of neural network architecture should match the complexity of the problem. Number two, Universal Approximation Theorem in practice. Neural networks with enough capacity, hidden layers and neurons can approximate almost any function. 3. Deep learning fundamentals. This tutorial demonstrates why deep learning gained popularity: the ability to automatically learn appropriate features from complex problems. Visualizing both datasets and training metrics provides crucial insights into model behavior. Hope you learned something quite interesting. In our next tutorial, we will show you a different example with PyTorch and deep learning. Until then, take care. Bye.